Hi. At this podcast, we're going to start introducing some of the gas laws. We'll learn about several different gas laws throughout the unit, but today we're going to start learning about Boyle's Law specifically. All right, Boyle's Law states that pressure is inversely proportional to the volume when you hold the temperature constant. We represent this mathematically by P1V1 equals P2V2. Pressure 1 and volume 1. Pressure is in atmospheres. Volume can be in either milliliters or liters. Here we see a molecular view of some gas molecules, and we're going to hold temperature constant so we can evaluate Boyle's Law, pressure and volume. So you see this little guy over here, little scuba man, he controls the volume of the box, makes it bigger and smaller, and then here's our pressure gauge and atmosphere. So those are the things I want you to pay attention to. So if we were to decrease the volume, okay, so make the box smaller, we see that the pressure increases. Okay, so decrease the volume, increase the pressure. Now, if you increase the volume, you see that you have a direct decrease in pressure. Okay, so if you give the molecules less room to move around, like when you're decreasing the volume, then that causes more collisions more often, which increases the pressure, the force per unit area. And then if you give them more room to move around, they're less likely to collide with themselves and the walls of the container, and so that lowers your pressure. All right, here's a graph. In this one, it is saying that the pressure-volume relationship ideally should be our 22.414, and this blue line represents an ideal gas. And you see that neon is has the behavior that is most similar to the ideal gas, whereas oxygen and carbon dioxide deviate more. So hopefully as we go along we'll find trends that will help us learn which gas molecules are more likely to deviate from ideal behavior. Here's an example problem. Oh snap, hold on, my phone's ringing. Alrighty, so you see that we have 20.5 liters of nitrogen at 25 degrees Celsius, 742 torr, and we compress that to 9.8 atmospheres at a constant temperature. All right, so by telling us our temperature is constant, that tells us that we are in no need of that temperature value. We're only worried about things that are changing. All right, this right here, this 20.5 liters, we know that liters is volume, so we're going to designate this as volume 1. Okay, and then we have 742 torr. 742 torr is pressure, so we know that that is going to be our P1. And it goes with P1 because it's associated with the first volume. Okay, and then this is compressed to 9.8 atmospheres. Atmospheres are pressure. Okay, so we know this is going to be our second pressure. Wants to know what the new volume will be. So that tells us that we are looking for our V2. Okay, so this is what we're trying to find. Now we need to make sure all our units are compatible. Alright, so we're looking for volume, so our volume answer is going to be in liters because V1 is in liters. Now these two need to be in the same unit. So we need to get torr to atmospheres. So we're going to use our pressure conversions to get this torr to atmospheres. Alrighty. So we have 742 divided by 760. That gives us 0.976. Alright, now we can go back and plug this all into our P1V1 equal P2V2 equation. All right, so P1, we have 0.976, okay, times V1, which is 20.5, is equal to P2, which is 9.8, times V2, which is what we don't know. It's like our X term. So now what you want to do is you want to, well, snap. I thought that was the eraser, y'all. That is not the eraser. Okay, so we have, we want to work this out first. 0.976 times 20.5. I got 20.008 is equal to 9.8 V2. So if we divide by 9.8 on both sides, okay, so that cancels that. So we have 20.008 divided by 9.8 is V2. That gives us 2.04. Now we need to sig fig it, and we see that our lowest number of sig figs is 2. So we're going to get 2.0. Our unit, go back up here, volume, liters. So we got 2.0 liters. All right. Let's look at the next practice problem. All right, we have 30.6 milliliters. So we know that's our volume 1. At 740 torr, so this is our pressure 1, is expanded at a constant temperature, so that tells us we don't need temperature, to 750 milliliters. So this is V2. Wants us to get the answer in kilopascals, so it wants P2. Alright, so we're going to plug everything into our little equation here. Alright, so we've got 30.6 times by pressure 1. Alright, so pressure 1 is 740 torr. Let's go ahead and get that torr to atmospheres. I just prefer to work in atmospheres. We'll end up converting it back to kilopascals eventually. So we're just going to divide by 760. That's what's down here. It kind of all ran together there. Alright, and I get, let's see, 0.974 ATM. Okay. Alright, pressure 2 we don't know, and volume 2 is 750. Alright, so now we're going to go back over here and we're going to multiply. So we have this times 9.974 gives us 29.8, and that's equal to the P2 times the 750. Divide by 750 on both sides. And that gives us a pressure 2 of 0.0397. Now, this was atmospheres. Remember, we were converted to atmospheres. But it wants our answer in kilopascals. So we've got to convert the atmospheres back to kilopascals. So we got 1 atmosphere on the bottom. And then our conversion factor for atmospheres is on top. Or not atmospheres, kilopascals. Alright, and that gives us 4.03. Now sig fig, we only have 2. So it's really just 4.0 kilopascals. Okay? Alright, and that's it.
Alright, class, what are we doing?
We are putting marshmallows inside of a vacuum, releasing the pressure so the marshmallows will expand. And then all of a sudden we're going to put the air back in and they're going to shrivel up. It's going to be epic.
Okay, let's give it a shot.
Awesome.
Alrighty.
Close the valve.
Whoa!
There we go.
There they go.
Oh, yes. Just as I hypothesized.
Overflow.
That's an overflow.
It's like popcorn.
My idea was epic.
It definitely is
Oh,
popcorn.
look at that one.
Look at the bottom there. They're all squished up
Look at
against
that.
the
It was
side.
empty and now look how full it is. And look at it. Look at it.
Look at that. Look at that jam packed
definitely
there.
is.
It's an air bubble right there.
It looks like string cheese. I can see it. Reminds me of Orville Redenbacher.
Keep on going.
Oh
The
man.
magical popping corn.
Look how big it is now, almost all the way full.
Except it's not.
Okay, stop it.
Greasing. It's
Release.
greasing.
And now we're going to release the valve.
Here we go. It's gonna be.
Look at the ones at the bottom. They all squished
That's some filled up stuff right there.
You are going to have fun.
Pretty
up.
sweet.
And then
The end product is not joke class. It is empty.
That was an entire package of small Jet Puff Craft brought to you